talk right now.
Yes, so hello, my name is Brysen Pfingsten. This is work done with my advisor, Jason Hemann, so I'll be talking about visualizing miniKanren search with a fine-grained small-step semantics. So we'll start out with a little introduction, a sort of thought experiment, then we'll get into the semantics, then we'll do a demo of the visualizer, and finally we'll conclude. So small-step semantics are a great thing. It lets you prove things like program equivalence, type soundness, safety. It helps with reasoning about your programs, which in a language like miniKanren, which is very declarative, is nice because your search strategy is coupled with your implementation. So if you were to want to understand that, you'd have to go read your implementation. So something like a semantics for that formalizes it is great. And implementation, the reduction steps themselves correspond with what you would see in your interpreter. And so it's been done for a variety of languages, including JavaScript, which is everyone here's favorite language. And so when you're building up a semantics for your language, it's really important to understand what your values are, because the values are the things you're reducing towards, and they're the things that you stop reducing at. So in Racket, you might put this expression into your REPL and get out that list. In Python, you might do something very similar. And in miniKanren, you could do a run query with the Pindo, and you'll get something that looks very similar to what you got in the Racket. So when you're thinking about your values here, you might be tempted to say, well, whenever I put something in my REPL, the values are the sort of things I get out. And miniKanren being an embedded language, you might say, well, my values are just the values of the host language. But if you actually implement miniKanren yourself, a more nuanced take would be that the values are substitutions. So we're mapping logic variables to the host language values and other logic variables. And the thing you see in your REPL is really just the reified version of that substitution. But I'm going to take that one step further and say the values are a tree containing success nodes and their substitutions. So the intuition here now is that we have expressions, which are trees, and our values are also trees. So at a high level, our semantics are just tree-to-tree transformations. So we have two contributions. The first is that small-step operational semantics, which is deterministic transformations of the search tree. They're operating at the level of individual goal evaluations, so we're operating below the level of the interleave, and we mechanize these semantics in PLT redex, and with that, we'll also validate some properties of the semantics. Secondly, we have a tree-based visual stepper, which is a web app, so there's no need for local installation, and we use those semantics at the core. So getting into the semantics, we'll assume some term language here. What's important here is our relation names are with R, and our variables are with X, so those will come up later. And we have the usual state consisting of a substitution mapping logic variables to terms and a logic variable counter. So we mentioned trees are our main thing, our expressions and our values. And so our program consists of some relational environment and some search tree. And our search tree could be empty, which represents failure. It could be a goal state. It could be a disjunction of two search trees or a conjunction with a search tree and a goal. Here, we'll look at goal states. So in order to understand our goal states, we have to understand what our goals are. And so for those, we have the T symbol, which represents success. We can unify two terms. We have disjunction, conjunction, and fresh. And so the semantics themselves are actually small enough where we can go over them in their entirety, albeit kind of quickly. So starting with our goal, the unifications. So for each example, I'll show you a pictorial representation, which is something like a minimal or most general example. So on the left, we have the rule for unify succeed. So if those two terms do unify, we update our substitution and we replace it with the success node. If unify fails, then we will replace it with that empty node. And for disjunction, we will simply distribute the state over the two goals. For conjunction, we'll give that state to the first goal and leave the second goal as it is. For fresh, we do the standard, we increment our logic variable counter, and we substitute the variables the user wrote with the logic variables. So visually here, you don't get to see much, but we evaluate that goal below the fresh with the updated state. Right, so coming back to our trees, so there's no strong way to motivate this, I think, except with an example. But right now, our disjunction is just a single plus, and so if we were to want to interleave those trees, we'd have to actually swap the order of those trees. So visually, what that would look like, and the actual tree itself here is important, but we have some tree that we're going to interleave, and we'd have to swap the two trees. And so visually, that can be pretty disorienting. You can imagine having a much larger tree or having nested disjunctions that you have to interleave. And so rather than doing that, we'll start with the tree, and The interleaving will simply change the route where evaluation is continuing. And so we call this the railway model because it's like switching the railway tracks. So rather than moving the actual tracks themselves, you're just switching which way they go. And so to do that, we just have two types of disjunctions, one facing right and one facing left. And we'll reserve that plus operator for our answer stream. So our answer stream consists of some answer appended to another search tree. And for interleaving, we'll introduce two control operators, delay and go. They're pretty obvious what they're doing. Go tells you evaluation can proceed down this tree, and delay just represents that tree is suspended. And one goal that I failed to mention, or I guess I delayed mentioning, is our relation calls. And they're special in that that is our delay points. And so now that we have all of our trees, we could start talking about our evaluation context. So the first one, EP, just steps down into the search tree component of our program. Then EA for our answer stream, we step past all the answers we've accumulated. ES, the third one, is for stepping down into the subtrees. So we follow our disjunctions. So for the left-facing disjunction, we go down the left tree. Similar for the right. And for the conjunction, we just go down the search tree component. And the one we'll be using the most is that last one, which is just a composition of the three. Right, so getting into interleaving, I mentioned that relation calls are our delay points. So whenever we encounter a relation call, we'll double wrap it with a delay and go. And the reason we double wrap it is because this will give us effectively a lazy expansion of a relation call. Because we know we're delaying it, there's no need to expand it immediately, especially in the visualization where that could clutter up your screen. And so this is when we would actually expand it. So after we interleave and come back, and we see a relation call with go on it, we'll grab our relation definition out of the environment and substitute the terms into that goal. Yes, and so this is the interleaving. So if we have, and also for the railway model, we're going to have some combinatorial effects. So here we have a disjunction, so we're going to have two. We have to handle the case where it's facing left and the one where it's facing right. I will only show the ones facing left, but the ones facing right are something like the symmetric version of what I'm showing you. So we have a disjunction facing out a delay, so we'll propagate that delay up above the disjunction, but we'll also flip the way the arrow's pointing. So you'll see here, it was starting left, we delayed, interleaved it, and now it's facing right. For conjunction, we simply just lift up that delay above the conjunction as we can't interleave conjunctions. And the way we get rid of these delays is, if you'll notice, we're matching on a different evaluation context. So we're only going into the program and through the answer stream. So we're effectively right below our answer stream. And so that means the delay has reached the top of the search tree, really. And so we can release it at that point. Yes, so that was interleaving. Now we could deal with some tree transformations. So the way we propagate our successes up, you'll see here we have nested disjunctions. And so the idea here is you have some nested disjunction facing at a success node. And so what we'll do is we'll lift that success node up and pull the other trees down. And so if we have a disjunction with a success node within a conjunction, it will either be a conjunction between that success node and the goal that was waiting, or the other tree and the goal that was waiting. And this is how we actually promote a success node to an answer. So once a success node reaches the top of the tree, it will say is now an answer and there's no more work to be done on it. And for conjunctions, if we have a success node, we need to take the state out of that success and evaluate the goal that was waiting in that state. And lastly, pruning, so we don't model failure within our trees. So as soon as we fail, we want to prune that subtree. So if we're pointing at a failure node in a disjunction, then we'll just get rid of it and evaluate the other tree. In a conjunction, we would say the whole conjunction fails. So that's the semantics part. Next is the visualizer. So there's some existing logic programming tools, like the bird box was very popular with Prolog. It's also called the 4-port model because you have those 4 ports, call, exit, redo, fail. And there's also and/or trees were pretty popular. The and/or trees are much more similar to what we'll be doing. We'll be showing an actual tree representation of the program. There has been some miniKanren tooling as well. So this work by Bird et al. A different bird, I'm assuming there's no relation. But what they did was they defunctionalized the higher order implementation of miniKanren. And once you have that defunctionalization, you have a first order representation, which is independent of any given search strategy. So you could do some cool things like have a user-guided search or neural-guided search. But theirs is a textual stepper, and it's not as granular as ours. So, demo time. Yes. So this is the UI for our website. So on the left-hand side, we have where you input your program, and the concrete syntax we accept is just the core miniKanren List-B scheme racket style. So we don't support things like disequality or the type-like predicates. On the right here, we have the tree canvas, which we'll see later. We have a sidebar to inspect the state information. We have dark mode if that's your thing, but I'm going to make you look at the light mode. At the top here, we have what step you're on and the name of that step. And so that's the gist of the UI. We have these 4 buttons: start, reset, back, step. So I'll go ahead and load a program from our list. And when we hit start, it will pull up the tree. And so one nice thing you can do is you can click on the node in the tree, and it will show you where it corresponds to in the source code. So this first fresh corresponds to the entire run query. This fresh would correspond to the first fresh in the run query. And we can click on the source code as well, and you'll see that it highlights the little unification here at the bottom. And a nice thing you could do with that is you can click on a node, and it sort of subscribes you to a state. And what I mean by that is as we step, it will show you in the source code where that state got moved to. So we are now on this fresh, and if we keep stepping, we have a long list of conjunctions, and so we're going to distribute the state down those conjunctions until we get to this first unification. We'll evaluate that, it will succeed. And another nice thing we have is that you can hover over a node and you can see its reified form. So being able to see the reification before it actually becomes an answer is kind of nice, because as you can see here, we know what the structure of the answer has to be without knowing its components. And that's something you see often is you conform the structure, or you constrain the structure to be something before you constrain the components of that structure. So here we have a list of 5 elements. And so if we were to click on this and open the sidebar, we could see that was added to our substitution. The first logic variable was a list with 6 elements with the empty list. And so as we step through, we can see, so let me step back actually. We can see that A has been added to the list, now B has been added to the list. Yeah. So if we step all the way up, we could see our answer is the list A, B, C, D, E, F is what we expected. So that's like tracing and looking at the state information. This program was from the last workshop, and it essentially just enumerates some little Indian byte vectors that are divisible by 3. So this is a fairly large program. So this will show you interleaving and how we lazily expand our relation calls. So if we step through, we'll get our base case, which is the empty list, and then we will expand that same count relation. And it's a pretty big tree. So we'll step through, we get another answer, which we can inspect as the list 1, 1. And we can keep stepping until we get down to this relation call. So if you follow the line down the tree, that will show you where the evaluation context is at. So we're looking at this relation call that we haven't seen before. So what we'll do is we'll add a delay and we'll mark it as go, which is green. And then we'll move that delay up, we'll interleave, so now the arrow is facing right, and then we can proceed evaluation down the right-hand side. And so you'll notice we haven't actually expanded the same count though, and we'll only get to it once either the other branch fails or succeeds, or if we encounter another delay. So here, we encounter mod plus 10, we add a delay, we push that up, and it hits the answer stream, and so we release that delay, and now we're facing the same count though, and we can continue evaluation with that. The last example is just the classic appendo, but with this one I want to show you a new concept, which is the trail. So if our first one's going to fail, but then we'll go down into it and we'll hit this unification. And so we'll see we unified the list miniKanren with cons logic variable 1, logic variable 2. So we'd expect 1 to be mapped to miniKanren and 2 to the empty list, which is what we see. But if you're keen, you saw this other part of the thing, which is the trail. And so the difference between a trail and a substitution is the trail contains the actual terms that were unified. So with the substitution, you're seeing the mappings that were required to unify them, but you don't see the actual terms that unified. And so that's nice because deep within evaluation, you might want to know that 1 and 2 came from unifying a list, versus here, it very well could have been 1 and 2 were unified separately. So that's good for the demo. Yes. Right, so this is how we would update the unify succeed rule. We basically add a new component to our state, which is the trail, the little T symbol, and then we update that when unify succeeds. We walk the terms and add them to the trail. So as I mentioned, we mechanize this in Redux, and so with that we can validate some properties by synthesizing programs and running tests against them. So one is that every well-formed program is deterministic, so we'll never step to more than one tree, and the other one is syntactic preservation, so you'll never step from a well-formed program to a non-well-formed program. And the nice thing about reduction semantics is that they're really modular, and so we also implemented depth-first search semantics, which you can really easily derive from the ones we did. In fact, if all you had was an eraser or a backspace key, you could take the semantics we had and create a depth-first search one. And what's nice about this is it runs on the same program base. So you could run the same program with a depth-first search semantics or an interleaving semantics, so you could show how a depth-first search would infinitely starve a branch, but our interleaving search wouldn't. And there's also another paper describing an operational semantics from miniKanren from Rosenblatt et al., and we implemented theirs. They just have more delay points, but we extended it with an explicit answer stream, the trail, and the railway model that you saw. So future work would be making it more of a debugger and less of a visual stepper. So you might want features like fast forwarding, you might want to step over a relation call, maybe some profiling features, breakpoints, etc. For scalability and UI, maybe stepping away from Redux and rolling our own implementation with nicer data structures can make it faster. You might, in the UI, want to collapse very large trees or the suspended trees. A user study, I think this would primarily be focused at students, seeing if students learn logic programming better with a tool like this. Some more semantics, so maybe something like a continuation-based semantics or iterative deepening depth-first search would be nice. And comparative semantics, so compare what we have to an existing implementation, possibly prove that they're equivalent. So to conclude, we've presented semantics, a small step operational semantics from miniKanren that makes the interleaving strategy explicit, and we use those semantics to build up a visualizer where the user can see the tree transformation step by step. We hope this will support clearer reasoning and understanding of logic programming and potentially some experimentation with some more semantics, and also for teaching students, I think it'd be a great tool. So a QR code for the tool is on the top and the source code is on the bottom. Thank you.
Okay, the mic needs some time to warm up when I switch it on. We have plenty of time for questions. Please ask questions. Yeah.
Hello, yeah, great talk and very cool stuff. One thing I was wondering, so right now, so I guess a sort of known issue with miniKanren is that when exploring disjunctions with the interleaved approach, some branches get much more time than others just because there's a sort of hierarchical approach. But I was wondering if you think the sort of railroad method could diagram two railroads that have more than two tracks, but then still sort of do the interleave stuff, and then so that you can have disjunctions of multiple things that is potentially a more fair search. Any thoughts about that?
Yeah, so right now our disjunctions are just binary. So there's only like one meaning there's left, or two meanings there's left and right. So are you suggesting like arbitrary number of, yeah, that could be interesting. I don't know what to say much about it, but yeah.
Thank you for your talk. I have a question. Why do you need different leftist and rightist disjunctions in your model, in your semantics? I think it only requires you to doubling some rules and don't don't give you impact.
Yeah, so it was actually something we added later. So we had a semantics that was just the one disjunction. But the reason I even showed you it was just to connect it to the visualizer. So the semantics and the visualizer themselves are very coupled. So I think, yeah. So there's other ways you could do it. So maybe you want to like keep a track of how many times this branch has been interleaved, and then based on if it's even or odd, you would know which way to go down. But yeah, you could derive a directly equivalent semantics by just removing that, and then during your interleaves actually swapping the trees. But it's primarily just for the visualizer.
Yeah, thank you. It's a very good work. Quick question about the back button. So you say you can set down, right?
Yes.
So to go back, are you using your small steps operational semantics here, or you just save the previous history in your front end so you can go back?
No, so there's no way you can know going backwards. So yeah, it's all just cached.
Yeah, so this is what I mean, like you save your history in your front end, so when you hit the back button, you basically go back to your history.
Yeah,
yeah, okay,
it's
thank
all
you.
cached, yeah. And if you step backwards and go forwards, that's also still cached.
A great talk and very interesting tool. I was wondering what the connection is between the front end and the back end. So, for instance, is the semantics that you showed, you said you mechanized in PLT-REDX. Is it that mechanization which is turned into the front end such that I could change the PLT-REDX code and have that reified on the front end? Or are they different, just kind of implementation of the same semantics, and I'd need to change the actual, I assume, JavaScript implementation in the front end if I wanted to, for instance, add constraints or lazy goals or something of the kind?
Yeah, so the front end actually does not a whole lot. Like, it really just renders the tree for you. That's about it. So if you wanted to add more operations or node types, that would be the semantics and the visualization are coupled. But yeah, I mean, essentially what you do is you have your program and you can serialize it as JSON and pass that over to the front end, and then the front end knows how to draw the JSON style tree. Did I answer that? Right.
Yeah, so if I understand correctly, the actual implementation of the stepper doesn't happen in the browser. It communicates with a back-end implementation, which is actually running the PLT-REDX implementation?
Yeah, so basically Redux provides a way where you can just say, give me the next step. And so you get the next step, you send that back, and then whenever the web browser asks for the next step, all it does is step the program one time, updates the state, and then sends it back over as JSON.
Great, thanks.
Just to try to add one more thing. I remember Wilbert make something sort of like relational things. So I'm still thinking about your back features. Like maybe if you use that, like you can implement the things like going back.
Yeah, maybe. There's definitely, how we're doing it now is definitely not optimized. There's certainly a better data structure because you're essentially rewriting just subtrees, but right now we're copying the whole tree.
Yeah.
So maybe storing like the deltas, like, okay, there's only this subtree that changed, and you can use that to reconstruct the previous tree would be more optimal. But you mentioned doing that relationally.
Yeah, like you make it relationally. Like you go back, you still can go back.
Yeah, I just don't know if you can reconstruct it perfectly going backwards. I think there's just not enough knowledge there.
Okay, more questions? Well, then I have the one. I played a little bit with your tool, and I got an impression that in order to understand what's happening, you need to familiarize yourself with the semantics. So you need to study the semantics first.
Mm-hmm.
Can you elaborate a little more about if this tool can be used to study the semantics without knowing the rules of reduction?
Yeah, so you're saying you need to understand the semantics to understand what's happening to the tree?
Yes.
I think the fact that it shows you where the evaluation is happening and also it shows you the name of the step, I think you can learn the semantics through the tool. So if you look at a tree it's a fun exercise to say what's going to happen next. And I think doing that repeatedly, you build up an intuition for what's happening with the semantics.
Okay, perhaps we need to test it on someone who doesn't know the semantics of miniKanren'.
Yeah.
Do we have any questions? We don't have more time for them. Thank you very much. And this concludes the third session. Thank you.